So now you know how to draw Lewis structures. And Lewis structures are three-dimensional structures that give you some idea of what a molecule might look like. So if we draw the Lewis structure for water, one of my favorite molecules in the world, and yours too, all life depends on this stuff. Here is the Lewis structure for water. And what we're going to learn to do is to convert a two-dimensional Lewis structure, just as this two-dimensional floor plan for a house is actually realized in the building of a three-dimensional house. We're going to turn this two-dimensional Lewis structure for water into a three-dimensional structure for water, and I'm going to give you a representation of that right now. So here is our three-dimensional structure for water. It's here are the non-bonding pairs of electrons on the oxygen, the two bonding pairs of electrons. And what you might ask is, well, why would water, from this two-dimensional structure that we've drawn, why would it pop out into three dimensions in this particular shape? And it's all due to what's called a model called valence shell electron-pair repulsion theory. And what it says is that bonds are made up of clouds of electrons. So there's a pair of electrons in each of these two bonds, and there's also a pair of non-bonding electrons here and a pair of non-bonding electrons here. And what you can see is that these electrons have spread out from each other to form this particular shape, which you're going to become very familiar with. So why would they do that? Well, valence shell electron-pair repulsion theory says this: bonds are made up of clouds of electrons, and those clouds of electrons have a negative charge. Each bond is made up of a pair of electrons, which create a region in space that's made up of negative charge. You have negative charges in proximity to negative charges. Those negative charges will actually repel each other. And so bonding electrons and non-bonding electrons that we have in a Lewis structure, these bonding electrons and non-bonding electrons are going to try and get as far away from each other as they can, because these electrons have this repulsive force between them. This non-bonding pair of electrons will try and get away from this non-bonding pair of electrons. But in the course of trying to get away from the non-bonding pair of electrons, this non-bonding electron pair runs into this bonding pair of electrons, and this non-bonding pair of electrons is repelled by this bonding pair of electrons, and these bonding electrons are repelled by each other. So this whole mess of repulsion, this negative repulsion, results in the electrons pushing themselves as far away from each other as they can get until they arrive at the maximum distance from each other. And that gives us the shape. That, in a nutshell, is what valence shell electron-pair repulsion theory says. And we call valence shell electron-pair repulsion theory VSEPR theory. Now, a couple of things that you're going to want to remember. Non-bonding electron pairs, they're only confined by one atom. So here's a pair of non-bonding electrons and here's a pair of non-bonding electrons. They're only attached to this one atom. There's no other atom out here that are confining these non-bonding electrons. And as such, they take up a little bit more space. And in taking up more space, they push on everything around it a little bit more. So these bonding electrons get pushed on by the non-bonding electrons a little bit more because the non-bonding electron pairs take up more space, and that's going to result in a difference in bond angles. So let's start out with the rules for determining the geometries for a molecule. And we have two types of geometries. First, we have the electron pair or electron domain geometry. We say that that's EPG for electron pair geometry. It's also called electron domain geometry because electrons exist in domains in space. The arrangement of the electron pairs around the three-dimensional space. Now, the electron pairs could be bonding electrons, it could be non-bonding electrons. It's simply everything that has electrons in it, non-bonding and bonding electrons. We often call the electron pairs, whether they're bonding or non-bonding electrons, simply things. And we're going to be counting things, which is all the bonding electrons, all the non-bonding pairs of electrons. The molecular geometry, or simply Mg, is a little bit different. It's only covering the bonding electrons, that is, the atoms that are around the central atom. So that's going to be the molecular geometry. Now, there'll be a condition where the molecular geometry and the electron pair geometry are the same, and there'll be a particular condition when the electron pair geometry and the molecular geometry are different. I wonder if you can guess when they will be different and when they will be the same. Let's find out. All right, so first of all, let's start simply. We'll draw the Lewis structure for our first molecule, and our first molecule is H2. All right, H2, each hydrogen only has one electron, so we draw the structure, the Lewis structure for hydrogen, and what we have is one bond. Well, since there's only one bond between the two hydrogen nuclei, it effectively makes a straight line. So we call this geometry linear. That is, where all you have is a straight line. And the bond angle between two atoms with a single bond between them, or a double bond between them, or a triple bond between them, is going to have a 180-degree bond angle. So from here to here is a half a circle. Circle is 360 degrees. Half a circle is 180 degrees. So if the molecule is linear, then the bond angle is 180 degrees. Any diatomic molecule, so diatomic molecules, H2 and N2, O2, Cl2, Br2, and F2, I2, all of these molecules are diatomic. They all have a linear geometry. N2 is a triple bonded molecule, but it's also linear. It's diatomic, so it has a 180-degree bond angle. O2 is a little bit different. It has a double bond, a couple of pairs of electrons here, but it's also just a diatomic molecule, so all of these molecules will have 180-degree bond angles because they are linear. Now let's use our drawing tool to see a visual representation in 3 dimensions of our linear molecule. You can see that our molecule, it's diatomic, and if I put one atom directly in front of the other, you can't see the other atom. That's because it's a straight line. The bond angles are 180 degrees. And the molecular geometry is linear. The electron pair geometry is also linear. Now let's take a look at carbon dioxide. So here's the structure of carbon dioxide. What you can see is a central atom carbon. You've got an oxygen on either side of the carbon. It's double bonded, but the double bonds don't matter. It doesn't matter whether it's a single bond or a double bond. It is counted as one electron domain, a single electron domain, whether it's a double or a single bond, and I count the things around the central atom. One thing, 2 things around the central atom. Well, when you have 2 things around the central atom, that's going to give you the electron pair geometry. So you count the electron domains only around the central atom, not around any of the satellite atoms, the surrounding atoms. You're only concerned with the geometry around the central atom. And we have 2 things around the central atom. And whenever you have 2 things only around the central atom, you've got a linear geometry. So again, you have a linear electron pair geometry. And notice, there are no non-bonding electrons on the central atom. If there are no non-bonding electrons on the central atom, then the molecular geometry will be the same as the electron pair geometry. It's going to be linear. Now let's go ahead and draw carbon dioxide using our drawing tool. And using our drawing tool, we can see that we have carbon and two oxygens. There are two electron domains. There's a double bond here and a double bond on the other side. There's no non-bonding electrons. Let's count the thing. 1, 2 things. That means we have an electron pair geometry, which is indicated here on our tool. That's linear. No non-bonding electrons, so our molecular geometry is the same as our electron pair geometry. Why? No non-bonding electrons. Our bond angles are a 180 degrees, half of a 360-degree circle. The molecular geometry is the same as the electron pair geometry if there are no non-bonding electrons. If there are no non-bonding electrons, then the electron pair geometry and the molecular geometry are the same, but only if there are no non-bonding pairs of electrons. And you can see there are no non-bonding pairs of electrons on the central atoms, so we have a linear molecular and electron pair geometry. This is a diatomic molecule, so it's always going to be linear. Now let's take a look at sulfur dioxide. The first thing we do, draw the Lewis structure. You can't determine the geometry of a complex molecule without drawing the Lewis structure, at least not easily unless you just want to memorize them all. So here is our Lewis structure for sulfur dioxide. The first thing we notice is that it's a resonance structure. You have a double bond and a single bond indicated, but you know from chapter 8 that whenever you have a resonance structure, they're absolutely equal to each other. That doesn't really have an impact on determining the three-dimensional structure in this case, so here we go. We've got a double bond, which we count as one thing. We have a non-bonding pair of electrons, which we count as one thing. So we got 1, 2, and then one more electron domain. That's our third thing. So there are 3 things around the central atom. So just remember that these electron domains are going to try and get as far away from each other as they possibly can. And the furthest away that they can get from each other is to arrange themselves in a what you might think of at, well, that looks like a peace symbol from the 60s. Peace, man. But in any case, they're going to split a 360-degree circle in equal values, or pretty much equal values. I'm going to ask you to remember something that we talked about right at the beginning of this video, and that is that we have a non-bonding pair of electrons here, and we'll talk about the impact that they're going to have in just a minute. So we have 3 things around the central atom. We take a 360-degree circle and we split it up into 3 equal parts. We come out with 120-degree bond angles. So what are we going to call this? Let's go ahead and draw with our drawing tool sulfur dioxide. We know we have a double bond, a single bond, and a lone pair of electrons. So here we are with sulfur dioxide with our non-bonding pair of electrons. And you can see that these electron domains are trying to get as far away from each other as they can, and there's 3 legs to this particular shape. Well, the prefix for 3 is tri, and we're talking about geometry, so we're going to say trigonal. But if I turn this right on edge, you can see that all the electron domains are in the same plane. So whenever we have 3 things around the central atom, we call the electron pair geometry trigonal planar. So the electron pair geometry is trigonal planar, but we have a non-bonding pair of electrons. And because we have a non-bonding pair of electrons, the electron pair geometry and the molecular geometry will be different from each other. So right now, what I want you to do is just pretend you actually can't see those non-bonding pairs of electrons and just look at the molecular shape that you see. And what you see is bent or angular geometry. So whenever you have a trigonal planar electron pair geometry, but you have a non-bonding pair of electrons, you get an angular molecular geometry. We also call that angular geometry bent, as indicated on the molecular geometry indicator here of our drawing tool. So you can see that this drawing tool that I've sent to you guys is very valuable in determining and studying for exam 4 and determining the molecular and electron pair geometries. So what have we got for sulfur dioxide? What you'll have to do on the test is count up the things around the central atom. Don't worry about the non-bonding pairs on the satellite atoms. It's only the central atom. So this will be 1, 2, 3 things around the central atom. We have a trigonal planar electron pair geometry. So the electron pair geometry, trigonal, planar, and the molecular geometry is bent or angular. Now there's one more thing that I want to say about the bond angle for sulfur dioxide. And to do it, I'm going to go ahead and use the drawing tool that we use. So here's our sulfur dioxide. Now, the bond angle is indicated as an ideal bond angle of 120 degrees, but we have a non-bonding pair of electrons, also called a lone pair of electrons, on the central atom. And remember, that lone pair of electrons, it's going to take up more space, and so it's going to push down on these bonding electrons a little bit more, and it's actually going to reduce this bond angle a little bit. It'll reduce it to about 1/16 because it's just going to push them together a little bit closer, because the non-bonding electrons, they have a little bit more room. There's not another atom up here confining the non-bonding pair of electrons by another positively charged nucleus, and so it presses down, and we have slightly less than an ideal 120 degree bond angle. Now, I won't ask you for precise bond angles on the exam, but I might ask you to know that the bond angles are a little bit less than ideal. Now let's take a look at boron trifluoride. Boron trifluoride, and the first thing you're going to want to remember is that boron is one of those electron deficient atoms that's happy with with less than an octet around it. In this case, it only has 6 electrons. There's no non-bonding electrons on the boron atom. So what we do is we draw the Lewis structure, we count the things, 1, 2, 3 things around the central atom. And with 3 things around the central atom, just like sulfur dioxide, we have an electron pair geometry that's trigonal planar. Since there are no non-bonding electrons, we know that the electron pair geometry and the molecular geometry will also be trigonal planar. The electron pair geometry and the molecular geometry, they're the same because there's no non-bonding electrons on the central atom. We can use the drawing tool to indicate that. So for boron trifluoride, we're going to go ahead and just put 3 bonds, no non-bonding electrons, and in this case, again, we have trigonal planar electron pair geometry. There are no non-bonding electrons, so our molecular geometry also trigonal planar. You can see it's trigonal because you've got 1, 2, 3 things around the central atom. It's planar because all of those things are in the same plane, and the bond angles are a perfect, ideal 120 degrees because these electron domains are canceling each other by staying in the same plane and pushing themselves as far out as possible. If they were to move down, it wouldn't make any sense. It would be energetically unfavorable for them to come out of the plane in this particular case. So they all stay in the same plane. Now let's take a look at ammonia, NH3. If you get to Chem 2, you're going to find out, and you should know now, that ammonia is a weak base, which has nothing to do with this conversation. But the first thing we do, as always, draw the Lewis structure. The next thing we do when we're trying to figure out geometries and bond angles, things like that, we count the things. We go 1, 2, 3, 4 things around the central atom. And if we have 4 things around the central atom, our electron pair geometry is a geometry we call tetrahedral. Tetrahedral. But we have a non-bonding pair of electrons, and that non-bonding pairs of electrons means that the molecular geometry and the electron pair geometry will be different from each other. Okay, here's our central atom nitrogen. We're going to put 3 bonds to hydrogen on it and a non-bonding pair of electrons. Okay, here we go. Now what we see with our electron pair geometry, 1, 2, 3, 4 things, our electron pair geometry is tetrahedral. So anytime you have 4 electron domains around the central atom, you have tetrahedral electron pair geometry. But because of this non-bonding pair of electrons, we have a molecular geometry that is different. We call it trigonal pyramidal or trigonal pyramidal. I think you can see with the hydrogens down here and the nitrogen here, it makes a little 3-sided pyramid. So if I were to look at it and put a plane over here and a plane over here and a plane on the other side, it would make this little pyramidal structure, and it's trigonal pyramidal because it's 3-sided. Now, what are the bond angles? Well, whenever you have a tetrahedral electron pair geometry, you have these 109.5 degree bond angles. Now, those would be the ideal bond angles for an electron pair geometry that's tetrahedral. But you know, you've got this non-bonding pair of electrons sitting up here, and with that non-bonding pair of electrons, you have bond angles that are slightly less than 109.5 degrees. So, if you have an electron pair geometry that's tetrahedral, the electron pair geometry determines the bond angles. What you're going to have are bond angles that are 109.5 degrees. And because we've got the non-bonding pair of electrons, those bond angles will be just a little bit less than 109.5 degrees. Let's go ahead and take a look at methane, CH4. You might recognize methane as being a compound composed only of carbon and hydrogen. That is a hydrocarbon. And you know what happens if you do a combustion reaction with a hydrocarbon, that is, you add oxygen to it, add a match, you get carbon dioxide, water, a bunch of heat, which has nothing to do with this conversation. So the first thing we do when we're trying to figure out the geometry and bond angles for a molecule is we draw the Lewis structure. Here's the Lewis structure for CH4, methane, and the next thing we do is count the things. 1, 2, 3, 4 things around the central atom. That means that the electron pair, also known as the electron domain geometry, is tetrahedral. And since we don't have any non-bonding electrons on the central atom, our molecular geometry and our electron pair geometry will be the same. They are the same when there are no non-bonding electrons on the central atom. So let's go ahead and let's build methane. Here is methane. Methane's a beautiful tetrahedral molecule. You've got 4 things around the central atom. All these electron domains are trying to minimize repulsions by maximizing their distance from each other. That's the essence of valence shell electron pair repulsion theory. We call it VSEPR. Valence shell electron pair repulsion theory. You're trying to these electrons are trying to maximize their distance from each other so that they can minimize the electron-electron repulsion in the different electron domains, and you have perfect 109.5 degree bond angles. So now I get to find out whether you actually watched the videos and learned how to draw Lewis structures and make a prediction as to the geometry. So here is a molecule that you've seen before that you should be familiar with. This is formaldehyde. We're going to draw the Lewis structure. So the Lewis structure depends on the number of valence electrons. Carbon has 4, oxygen has 6, each of the hydrogen has 1, but there's 2 of them. So that's 2 times 1 is 2, plus 6 is 8, plus 4, that's 12 valence electrons. All right, carbon will be my central atom. I'm going to go ahead, put my hydrogens out there. There's my hydrogens. And I'm going to put oxygen up there. And I'm going to go ahead and populate this with electrons. Everybody wants 8 except for hydrogen. And let's count them up. 2, 4, 6, 8, 10, 12, 14. Oh my gosh, I used 14. I only have 12. I'm 2 over, so I need to make another bond. So I'll go ahead and I'll make that bond between oxygen and carbon, because you know you can't make a double bond with hydrogen. Why? Because hydrogen can only have one bond. Now we're going to count the things around the central atom. 1, 2, 3 things around the central atom. 3 things. That means that the electron pair geometry is what? It's trigonal planar. Now, the question of the molecular geometry depends on whether there are any non-bonding electrons on the central atom carbon, and we see that there aren't. Since there are no non-bonding electrons on the central atom, the electron pair geometry and the molecular geometry will be the same, trigonal planar. And if you watch the videos and you work the problems, you've got yourself 100% as a class. Oh, one more clicker question, one more opportunity to get points. So phosphorus has 5 valence electrons. There's 3 hydrogens, so that's 3 times 1, 5 plus 3, 8 valence electrons. That's going to put phosphorus here. I'm going to have hydrogen and hydrogen. Go ahead and put the bonds on them. Hydrogen. And there's a non-bonding pair of electrons. Phosphorus has 8. Each hydrogen has 2. 2, 4, 6, 8. Done. There's my Lewis structure. Count the things around the central atom. I've got 1, 2, 3, 4 things around the central atom. That means that the electron pair geometry is tetrahedral. I'll just write, oh, there we go. Tetrahedral. And then the molecular geometry is going to be different. Why is it going to be different? Because of these non-bonding electrons sitting up here. The non-bonding electrons are going to make the molecular geometry different. When we look at the molecular geometry, we only look at the bonding electrons, and that's this shape right here. And if you see, that kind of looks like a 3-sided pyramid, and we call that trigonal pyramidal. So the question is, what is the molecular geometry? What is the molecular geometry and the electron pair geometry? So the question wants the molecular geometry first. That's trigonal pyramidal or trigonal pyramidal. And then the electron pair geometry, that's tetrahedral. So we'd find trigonal pyramidal and tetrahedral.